So with that, this topic is actually quite interesting to me, so I'm not shocked that the room is full. I'm sure Dr. PCB back there will have a couple of comments or two about this topic as well. This is about passive components, and it's both active and passive components when we talk about embedded components for this topic with Juergen Wolf. So Juergen spent a few years as a design engineer with Bosch, but now with the board business for, what'd you say, 3 years now?
No, actually 9.
9, geez, I'm sorry.
Already.
3 years at Bosch, 9 years at Wirth. And so obviously a guy with a lot of experience and a credible name, obviously. So Juergen Wolf.
So thanks, Lawrence, and thanks all to you being here, looking on embedding of components. And so just for a starter, so in the ballroom half an hour ago when this topic was being announced, there was a guy sitting 2 seats beside me and telling to his colleague or whoever it was there, well, embedding of components, it's really nice, but it's a heck of expense you have to do. It's just too expensive to do. Maybe. We will see in this presentation why there is an advantage of using this technology. And so therefore, let's go to the agenda. So in the beginning, to get every one of you on the same level, I want to just give you a brief overview of the advantages, why to use embedding, and why to embed components into printed circuit boards. We will have a short lookup of the technologies. So there are different technologies out there in different variations and stuff like that. So a lot of board manufacturers already offer one or the other technology. And I will go to some just quick process flows which go on top of the standard PCB manufacturing and give you some microsections so that you actually see how it looks like. Then we will go on to the procedure. So a lot of people ask me, how do I go on with such projects when I want to do this? So we'll have a look on that. And then we really switch to Altium. So I'll give you some hints, some tricks directly in Altium about the part library, layer stacks, placement, one specific part, solar resistance, solar pastes on inner layers. We will see why we need that, and part outlines. So that's the program for the next couple of minutes. So let's go to the advantages. Why do you want to do this? So basically, the biggest trend worldwide why people are embedding components into printed circuit board is basically the miniaturization you get. The miniaturization is done in different ways, actually. So the biggest worldwide trend is so-called package replacement. So you use the PCB technology, and the technology is offered in this process house, you could say, to just embed components. Take an active die, combine it with PCB technology, and make a new package out of it. Why would you do that? Well, actually, we are working on a big panel. It's like a standard panel is 18 by 24 inch. So you get a lot of components being done in parallel compared to a lead frame technology, for example. In addition to that, we still can rely on those standard PCB technologies, which means you can make through holes, for example. So you can have a package. On the bottom side, you can have your connections. And on the top side, you, for example, can add pads for the next set of components. So you can make real system in packages very easy with that kind of technology. So that's one part of it. But the other part of it is like, you can save space. So I have a lot of customers who have like a new product coming up or a new evolution of a product, new functionalities introduced in a new product, but they lack the space due to the outer housing. So what you do, you can go to the inner layers. You can have a third or maybe even a fourth layer for assembly of components to fit everything to your application. The second part is the performance or the function of the board. We can have an integrated shielding, and we had this in, for example, for Dr. PCB. So even for the passives and actives, we can use the copper in the PCB to shield the components. So there is no metal housing on the outside and so on. Then we can have short signal paths by, for example, placing decaps directly underneath components from the outer layer. And we can have a protection against plagiarism. And this actually is being done in several kinds of ways. So very easy way, for example, is customer of mine is embedding 0402 resistors underneath 0402 resistors. So from the outside, you do not see those components anymore. Even when you go to the X-ray system, you hardly see them if you have a good operator. And you look to the edges of your X-ray picture, and maybe you will see that there is something different, but you cannot grab it quite good. You only will see them when you really make cross-sectionings or go to the computer tomography. But this really goes on in several ways, till up, for example, embedding RFID chips directly connected via I2C to your circuitry with switches in the RFID chip, storing data actively on the RFID regarding production numbers, regarding lot numbers, regarding revision dates, regarding calibration dates, and so on and so on. And the last point is basically the reliability, and this is where all the automotive guys, medical guys, and even military guys come into the game, because embedding of component enhances for a lot of applications the reliability. So for example, we can have a protection against environmental influences. So we have several projects running at Würth where we make, for example, sensors which go directly into the box of your gear shift. So it's directly in contact with oil. And every one of you knows, especially during winter time, when you heat up the car, when you start the car, well, especially in northern countries, when you have minus 20, minus 30 degrees Celsius, you heat up the car and it goes up, the oil up to 105 degrees Celsius. And this is each day in the morning and evening, the next 10 years. So it's quite a big temperature range every day, every year. And what happens is you have different materials and each material acts differently. So you have a different coefficient of thermal expansion, CTE, between different materials. And in previous works, when we look at those gear shift box sensors, those have been standard double-layer PCBs. There were some Hall sensor ICs on it, some caps, some resistors, nothing critical, nothing complex. But they were sealing those components with transformals. And the PCB and the transformal, they just have different CTEs. So this is working against each other. There will be a crack for sure. And this crack is wandering to the inside. And as soon as this crack reaches either a component or a track, the oil will dissolve the copper, and the sensor, or whatever it is, will be gone. So by embedding the components, we could get rid of this transfer mold. Everything is being inside PCB material, so you do not have two different materials working against each other when you look from the outside. You for sure have your components and the PCB material, but that's a different topic. From the outer layers, you have one material, so this crack won't occur that fast. So we could increase reliability by times 3 or 4 with that setup. Then you can have a secure fixing. This is where, for example, military and so on comes into the game. And it's easily explained by, for example, looking at a capacitor, a ceramic capacitor fixed on the surface of a board. You have 2 solder joints. When you embed the component, you have still 2 joints. It doesn't matter in which technology, you have 2 joints, but you have material surrounding the whole component. So the way how the force acts on that component is completely different because it acts on all surfaces of the component. In addition to that, by embedding the component into the printed circuit board, it's getting closer to the neutral line. So even bending and stuff like that is reduced in regard of mechanical stress to the component. And the last point basically is the thermal management. This is where all the MOSFETs, IGBTs come into game. There are some IC manufacturers already out there who can work with copper on their bare dies. So we can directly connect them with the copper from the PCB. So we have a direct copper connection and a very good way how to get the heat out of the boards. So when you look on a worldwide global trend, so basically the package replacement is one part, especially well being used nowadays in the smartphone industry, as well as the short signal path. For example, every one of you who's using an iPhone of the newest generation or a Samsung smartphone with an Exynos processor is actually using that technology. Because in the processor substrates, you will find the decaps already in the processor substrates, so that like Samsung and Apple do not need them anymore on their main board. So you're using it already. But how it's being done, that's the question always. So there are basically worldwide 3 different technologies. One's, I just call it ET solder for embedding technology solder because it's based on a solder technology. It's pretty straightforward because basically you use what you already know. And what do you know? You know components on the outer layers being soldered onto your board. But now we do not solder them onto the outer layer. We want to solder them on the inner layer. And we can work with active and passive components and basically use a very wide range of components which is known from the SMD area. There are some components which cannot be used. For example, if the component is just too thick, that it doesn't fit into the board. So if you want to embed a 2 millimeter thick capacitor into a 1.6 millimeter thick board, that doesn't work. Or if it's a component with liquids inside, for example, or with air access, or even air-sealed components. There are some regulations and restrictions, but a huge range is being usable in that area. Then there is the so-called microwire connecting technology. This is where it's getting more specific. Here we still can combine active and passive components, but those components, they need to have a specific metallization. So they need to be compatible with microwires so that you can connect them with microwires. And unfortunately, this doesn't work with standard SMD components. So you need to have components, either active or passive, who have a copper termination, who have a copper pad, or for actives, for example, a nickel-palladium pad. And there's a third technology which relies on a specific flip chip process where you embed an active die directly into your built-up in a flip chip kind of way. So how would these process flows then look like for these different technologies? So first, I hope the ones in the back see this as well. If not, you will get the slides for sure. But what is being done is there is an inner layer core, and this inner layer core looks like any other inner layer core, plus we need to add a solder resist to do the soldering, and we need to add a solder surface to do the soldering. The solder resist usually is not being done fully covering on the panel. Those are just some small frames in the area where you really need the functionality of the solder resist. And the solder surface actually is something like tin or whatever, not gold, because gold won't combine with the resin from the printed circuit board later on when you do the lamination. So you need to have a solder surface which actually acts as an adhesion promoter for the lamination afterwards. But after the assembly of this thin core, we go to the lamination step. So this is step 3 here in that case. So we take cut-out prepregs, if these are routed or punched or whatever, doesn't matter, but they need to be cut out in the area where the components sit. So we create like a virtual cavity for those components so that they won't be destroyed in lamination. How will they be embedded? This actually happens during lamination. So these cut-out prepregs, they still have a free amount of resin, how we call it. So the resin starts to flow at a specific temperature and a specific pressure, and is surrounding those components completely. And after the lamination, actually the board looks like any other printed circuit board. So from the outside, you do not see any difference. And all the other remaining processes are just like any other PCB. The only difference for us as a board shop is now we have to deal with electrostatic discharge. That's pretty new, so not a lot of board shops have this. So that has to be introduced in the board shop. But other than that, the board itself looks like any other board. So you can handle it and treat it in your fab when it comes to outer layer assembly and so on, like any other board. In principle, the microwire technologies are almost the same. The only difference is here we are not relying on a soldering technology. Here we are relying on an epoxy gluing. So we glue the component directly either onto a copper foil or it's being glued to an inner layer core. Then we do a lamination, just like in the solder technology. So we cut out a prepregs, do the lamination. The difference now is the connection style to the component. For the microwire technology, as the name says, we are drilling vias with the laser down to the metallization of the component. And then we put the whole core into our plating system and directly plate copper to the connection of the component. So we have no solder inside, we have no bumps, no gold bumps and whatever inside, which makes it really high reliable in that area because you have less interfaces. You have a direct copper connection. Copper is actually much weaker and not so brittle than solder, so this is an increase in reliability. But as I said, you need to have the components compatible with that one. And the third process flow is actually almost like the solder technology. You take the inner layer core, then you assemble the flip chip onto the inner layer core, you cut out your prepregs and put it into the lamination press. So coming back to that argument, like now almost 1 hour ago, the technology being expensive. So when you sum up this process flow, what is in addition to a standard PCB? Actually, it's only a few processes more. The assembly is like the same cost on an outer layer assembly, so you can calculate with that one. You need one solder resist process more, you need a solder surface process more, and you need to cut out those prepregs. And that's about the additional cost. Nothing more, nothing less. Yeah?
If I might ask a question, what about test? Who owns the liability in terms of test?
That's a very good question, normally being placed at the end. So testing is actually being done in different stages, depending on customer requirements, depending on the application. So we either test right after your assembly, but often it's not possible due to missing nets. Then you can test after the lamination, but still that might not be possible due to missing components. So it's actually always a discussion when to test what. Do you use an adapter? Do you use finger probe testing and so on? So there are all different kind of ways how to deal with that. But you need to talk about it really in an early phase, because testing here is rather critical. Even when you want to test after lamination, the designer, the layouter has to think about test points being visible on the top and bottom so that you still can access those components. Okay, so just to give you a little bit more insight, I tried to use Altium for a small animation. So how does it actually look like? So this is a cutout of a printed circuit board in a layer. And what we do now is we print the solder resist frames. So you see the frames surrounding those solder pads. And we add the solder surface, which acts in both ways. On the first hand, as a solder surface, so you get the wetting from the solder. And on the second hand, we need to have an adhesion promoter for the multi-layering. So every printed circuit board shop needs to have an adhesion promoter on the copper. So it's not just pressing it together, because copper doesn't want to stick to resin. So we need to have an adhesion promoter. And in that case, it's a combination. So the solder surface is the adhesion promoter, so it's no additional process here in that case. So then we go to the layup. We normally start a bottom-up approach. So we start with the copper foil. We add the first prepreg. Then we have the assembled core, like you see here. And then we have those cutout prepregs stacking on top, and you see those cutouts so that the component fit into those cavities later on. So everything is being stacked up, and you can even make like stacked cavities. So if you have components who are thicker than others, like shown in here, you can make even stacked cavities. So this component is thicker, but it needs a precise planning to do so, because here in that case, it's not allowed to have a routing on these layers. So this needs to be chosen and described correctly. And then, as you see here, this is later on just being treated as any other board. We do the structuring of the outer layers, vias, solder resist, and so on. So how does it actually look like? This is always really, really interesting, and I tried, especially for those two ones on the left side, the solder technology and the microvia technology, I compared 0402 resistors in that case. It's the same size, and what you actually already see is here, the solder fillet. You do not have this one here, so this is space being saved. What you see, the difference in thickness of the component. As I said, we need to have special components. Those components are provided already by several manufacturers like Kowa, or for the passives like Murata, like AVX, and so on. So they're offering passives with copper termination. And you see the microvias directly connecting the component from the top, not from the side. For the flip chip technology, it's a little bit different. Here we're relying on active components, which are already being bumped with gold bumps, so that we have a connection here in that case with the gold bumps directly connected to the pad. If you want to have more details, we can talk about that later. That's just a lot of stuff going on there, and it's just a lot of time. But to see the differences, you have those microsections of those kind of things. So how is the procedure for new projects? And at the moment, it looks like that we need to have like a lot of data to have an idea what we actually want to do. So it's often when you come from a previous project and you already have your bill of materials, what we offer as a service is that we check. We check your BOM and have a look on the components and are looking which components are actually being embeddable. But to do this, we need to not only have the BOM, we need to have now precise information about the mechanical dimensions of these components. So we always calculate with a maximum, so we need to have X, Y, and Z plus their tolerances, because especially in the z-axis, we definitely need to know what is the thickest we can get so that we can calculate a stack up out of it. As I said, all the mechanical tolerances. If already exists an existing pick and place file and some planned assembly drawing, so what do you think already, if you have it, where to put components? The board outline is very important. We've seen this in several talks already in the last 2 days because board outline is directly linked with our manufacturing panel. So how many boards can we fit onto our manufacturing panel? Do we need an array for the assembly of the outer layers and stuff like that? That's what we really need in an early phase to save you cost and to maximize the amount of boards we can fit on our production panel, and so on and so on. And what we do with all this information is we give you a first stack up. So we think, okay, regarding those components, regarding your requirements, you'll get a stack up. And especially what we need is required layer connections. So from which to which layer do you want to connect inside the board? Do you have any predefined spacings? Like, do you have impedance control board? Do you have insulation requirements and so on? So that everything can be planned into that given stack up here. So actually, this is what normally goes on. So regarding all those parts, we start with a hand sketch. Say, okay, where does something fit? Where can I have what? And so on and so on. And based on that hand sketch, we create, or every other manufacturer creates a stack up based on that. So now, let's go to Altium. Now it's getting interesting. How do you actually do it? So regarding the part library, a system like Altium is really good to have it because nowadays you can have central part libraries and those footprints may be moved from layer to layer. What does I mean with that? So I just tried to take, again, an 0402 resistor to not make it too complicated. But we have our schematic on the top. We have the Altium 3D view and the description. So what we just do is we move this resistor onto the inner layers. So by just 1 or 2 clicks, you can move it in your stack up. And this is just a few clicks, and you can really drive it through the stack up. And how it's actually being done is you need to take care of your stack up manager. So in the layer stack manager, you define all the layers. And what's important is this one here, the orientation. Here you decide on which side the component will sit on the inner layers. So as you see here, top layer, bottom, okay. But on this core, we can have top, bottom as well, and on this core, we can have top and bottom as well. So when you go to the component and to the component manager dialog, you see that there is the layer, and up to now, you just chose top and bottom. Nowadays, in Altium, you can choose actually the layer where this component has to sit. And Altium is directly turning it around in the same way as you have it from going from top to bottom. So it's being flipped automatically. If you want to override that, there is still a check which you can do, flip on layer, but that's not advisable. Because if you have if you have the stack up correct in the layer stack manager, you do not need that one here because it will automatically flip the component on the right layer. So let's switch to Altium so that I can show you this one here. So I just prepared a board with this one resistor. So when we go to the 3-dimensional view, so you see this sits on the outer layer. So if we want to move it to the inner layer now, come on. So we just switch in the component dialog. Let's say we want to move it to layer 3. And that's about it. It's down on layer 3. It's that easy, that simple. Luckily, now this works. Like 5 years ago, I'm working on this technology since 2009, 2010. That was a pretty hard job for a layouter to realize this. And even if you're working with a tool which is not capable to do this, it's hardly not manageable. Here, it's rather easy. You can have the component on the inner layer based on your stack up manager, on the layer stack manager. What else do we need? We need to have additional parameters for the PCB processes. So it's always good to have some kind of cavity surrounding the component. So we need to have some free space surrounding it, and we need to know the 3D body. As I said, we need to have the z-axis. We need to have this calculation. So it's always good to add something so that we know what actually the component needs as a free space. So you can talk to your board fabricator, say, okay, how much space do you need surrounding the component? Is it 100 microns? Is it 200 microns, or whatever? And then you can use a mechanical layer, basically, to add this. In addition to that, it's important for you, for the three-dimensional view, that you can have a look on this cavity and see what it actually looks like. So you can like make a region surrounding that component. Then you go to the region manager, and you change the kind attribute to the cavity definition. So this is what it looks like. So you can choose cavity definition. You can choose the mechanical layer you want to put this onto. And in addition to that, you can set a height attribute. And the height attribute, as I said, we need to have the 3D body. In addition to that, for soldering, yeah, for sure, you need to have a standoff. You need to have a clearance on top. And this is rather really needed, because we already had, in the early times, boards where components were touching the next layer due to whatever reason. But if there is copper, or for example, for a passive component, the copper reaches the component, you can get shorts. So you need to have a clearance on top so that this doesn't happen. And this clearance is somewhere between 50 and 100 microns. So everything sums up then. And I just took one of these components. This is a Panasonic component now. Can choose every component. It's just by chance what I did. And you look into the data sheet, and there it says thickness. Down there, it's 350 micron thickness, plus the tolerance, which is 50 microns here. So we already see the component can be 400 microns, even if it says 350 as a nominal value. Then you take the standoff, you take the clearance, so you get the cavity height, 485 microns. You can put that value into the height attribute here, and you get the right cavity. What happens now for Altium and for us as a board manufacturer, you get a so-called managed stack. So you see, when you go to the layer stack table, there will be new stack up. So we directly see, if we put all the distances and stuff like that inside, we see directly the cutouts we need, the virtual cavity we need to create for this component. And for you, in the view mode, in the 3D layout mode, you actually see this cavity inside the board so that you see how much space is needed for that one. So again, let's switch to Altium. And we already see it here. So when I just move it around a little bit, you see the hints that this cavity, and that's why I moved the component to the edge, for you to see actually that there is a cavity being created by Altium, so that you see the component sitting inside and the space you need for that cavity. When we go to the 2D mode, and I just zoom out a little bit, I placed already the layer stack inside. So now, based on that component, we see this. And let's switch back. I just move the component to the outer layer again. Doing the layer stack again, and you see the additional stack just disappeared. So it's a managed stack based on what you put into your layer stack manager. Again, we go back, put the component onto layer 4 this time. Let's look on the new stack up. And you directly see there is this new stack where we see as a board manufacturer which cavities do we need. So that's pretty interesting to have this, especially for you as a check, a three-dimensional check. It's unfortunately not yet automized, so that would be one feature I would really like Altium to have in future, to have like a three-dimensional stack, a collision prevention for the components on the inner layers. But it's a first point and first possibility to check if everything is okay regarding z-axis dimensions. Okay, going back. What else do we need? For the solder technology being offered by several board shops already, we need to do a soldering on the inner layer. And the soldering on the inner layer, we need to have the solder mask. There are some who try not to use solder mask on inner layers, but when it comes to critical layouts, you need to have a solder mask to get rid of any shorts and so on being created by the solder, as well as the solder paste on the inner layer. So up so far, no EDA tool I know out there on the market is capable to even create inner layer solder mask and inner layer solder pastes. This would be the next thing I would really like to have Altium being offering in the future, so that it's easier to create such boards. At the moment, you have to overcome this intricacy by introducing again another mechanical layer. So this is what it actually looks like from a manufacturing board. Here you see the copper traces, and those small frames surrounding your pads. So these are 100, 150 micron frames, 75 micron even when it's once getting very tight in space and so on, but nothing else. So the remaining parts is still the metal. We do not want to have more solder because reliability will just be much higher if we just use the solder mask in the area where we need it, and the delamination risk is reduced by a lot. Okay, but how do we do it? Yeah, as I already said, we would add additional mechanical layers in the library already, and for us as a board manufacturer, you can give out those mechanical layers in your Gerber data or in your ODB Plus data so that we see what we need. And the same one here in the layout again for different components, you will get this here. So again, let's switch to Altium. That's wrong. So that's one here. So I just prepared a sample board. And what you see here is an inner layer, layer 4. So we switch to a predefined view. And I predefined just the inner layer, layer 4. And I have a mechanical layer. In this case, I renamed it to solder resist layer 4. And this is actually what it looks like. So you can have those small frames. And the only difference from an outer layer of solder resist is that negative, positive. So on the outer layer, you normally, when you draw solder resist, this is the area where you do not want to have solder resist. In that case, it's easier because you're drawing the frames. It's easier to draw where you want to have solder resist. So that's one difference. Oh, why did it change here? Okay. How this actually is being done, basically, yeah, you're just drawing a frame surrounding your pads and so on. So that's rather straightforward. So what else do we need? Solder paste, but solder paste basically is being done just like the solder resist. So you have a next mechanical layer and put your solder paste directly onto the pads as you want to have it. Unfortunately, not automized yet, hopefully in future. What else do we need? As I said, we need to have a precise information about the part outline. Part outline is critical because we need actually really to know where to do the cavities. And I just took a picture after assembly of such an inner layer. You see this SOIC here. Here we have the epoxy body. So this is what every one of you knows, the black part. But for us, during embedding, not only the body here is important, we really need to know everything about the components. So each gull-wing, each J-wing, and so on, we need to know the really outer dimensions because you don't want that these joints here will crack because we just calculated this body. For the cutouts, we need to calculate each part of this component. So how is this being done? Again, it's rather easy and straightforward. We need to have the actual body, the contacts like the gull wings or the J-leads, and the pads. So then we are sure that each part of the component is being cut out in the prepregs. And this is very easily being done on a mechanical layer as well. So you just, like this purple area here, you just fill in the mechanical layer out regions so that everything is being covered, the body, the contacts, and so on, so that we know this information when we get the data. Because what do we do out of it? We'll still see this later. We create groups of cutouts. So we are not cutting out each component individually. we make like groups, or we want to make groups so that we have one big cutout, and all the resin can flow into that big cutout. Again, in Altium, switching back, this is what I've done in this, this next few parts outline. So this is what then afterwards it actually looks like. So we see the parts with all their joints and so on, and if we take this and put it onto a big panel, we actually see how we can group this stuff, and our CAM engineers can work with that one. It's always the max tolerance. We always calculate with the max tolerance of the components. Yeah.
But what about pick and place variances? Do you have to take that into consideration as well?
Yes, definitely. But it's basically the pick and place is just like on the outer layer. So we can give you our design recommendations based on that one, yes.
How good are the vendors' step files? Are the step files good enough to verify, particularly during the design phase, for collisions? Or these step files, because I assume they are always showing the nominal values?
Yeah. They always show the nominal values, which is, for some components, not easy for us. Yes, that's true. So and this is something the designer or the guy who's making the library really needs to take care of, that we have the maximum information in the BOM. So that there are additional parameters, X, Y, Z, plus the tolerances, so that we can work with that one. So we have scripts already in the background which are analyzing the BOM, trying or calculating the maximum component thickness if we have both values, so nominal value plus maximum value, so that we can do a calculation behind that. Because what we do now, what you do not see as a board manufacturer, we have a script, for example, which is calculating the occupied volume from the components, and is comparing this with the volume from the cutouts, and with the volume of free resin we could get from the prepregs to see if we can embed everything in void-free, so that you do not get any air entrapments inside of the board. And yeah, 3D models, step files is normally a nominal point of view. So it's for viewing, it's okay, but for an actually check, it's not that easy to use, yes. You definitely need to know what you're doing. So we have huge experience. We know from each prepreg which we use, what's the amount of typical free resin which can flow. So a prepreg, I just go on a little bit wider. So a prepreg, most of you hopefully know, is like a glass cloth and pre-impregnated with resin. So it's hardened already a little bit so that it's not tacky anymore. So you cannot use every part of this prepreg. So we know like at 1080 how many % of the resin will flow out there. So it's basically a three-dimensional calculation, how many free resins you will get from the prepregs you're using, and from the volume you have in your components and the cutout. So you can calculate on one hand, is there still enough resin to fill everything? That's one part. The second part is we know exactly how far these resins will still flow. So they need to go underneath components, on top of components. They need to fill spaces. And you cannot populate like the whole area and have the resin flow 2 centimeters. That wouldn't work. So there are restrictions behind that we know. And actually, this is something on the last slides, that there is a restriction in the grouping of the components so that the resin can flow on each area so that everything is being covered and void-free. Actually, no. You will see that example later on. So there are some restrictions. So at the moment, we are bound or tied like to 40 to 50% population on the inner layer. So we cannot do more at the moment because we still need the resin coming out from the prepregs. But you can populate groups. And those groups, they can actually be quite big if you know what you do. And we will see this on the next slides. So let's switch back. Because that's actually now on the next slide. Components need to be grouped so that you like get not single cutouts. You need to get a bigger cutout, but the cutout is not allowed to be this huge. So we know that we need to have a space, or turn it around. Every area or every space inside this cavity needs to be reached within 5 millimeters. So this can be 1, 2, 5 millimeters or centimeters long, but still from every edge, there need to be one point where you can reach the inner layer, or the inside of this area within 5 millimeters. So when you do a look on this like that, so this would be too much, that would be too much. But there are areas where you can reach this specific point within 5 millimeters, and then it's OK. So you can make, for example, long cutouts, and still the resin can flow inside. But this is something we really need to know. So you cannot make like a 2 by 2 centimeter cutout. There are maybe some ways to overcome this rule, but this is when it really gets close into detail. We can make something like, in a multi-layer stack-up, we call it, it's almost like venting holes. So you can make holes into a core so that prepreg can come from the backside as well. But this is when it's getting really tight and really complicated in calculation of the resin. So from a starting point of view, it's easier to calculate what is coming from the side to the inner layer. OK, and this is an example. So it's not 2 or 5 components which can fit inside. This is actually, for example, an area 1 by 1 centimeter. So you can fit quite a lot of components inside that area. And this is a radio module, actually, where a lot of components are already being embedded inside. And you see there are not much components and not much connections to the outer layer. There are some pads out there, but it's quite populated inside. And still, following all the rules, we can completely fill this one here with resin without any voids. There are design guides, design rules. I won't go into that detail here. So you can download them from us or from any other board manufacturer dealing with that. So I hope I could show you some tricks, some hints, some information about the technology. And thank you for being here.
Yay, absolutely. I thought it would be interesting, and it was interesting. Does anybody have any questions? If you do, yeah, please use the mic so we can capture it for virtualization.
I've got 2 questions, actually. First, on if you're using a V-groove, and therefore you're going to cut out on a... Is there restrictions, therefore, now on where you can place components inside? Because obviously you're going to actually have more stress.
So there are restrictions how close you can place components. It doesn't matter it's a V-groove or it's a routed edge. There are specific distances you need to take care that you're away from the routing path.
And the other question is concerning magnetostriction of ferrite components.
Ferrite components, we tried that one, but it's really critical. Ferrites are very, very brittle, so normally they tend to break when you want to try to embed them. There is an overcome, so we have several products running with that where we create really a cavity inside the board so that they are not attached inside. They can move around inside, so with tolerances and everything, so that they can move 100 microns. But that's not what you really want to do, yeah. Because, yeah, ferrites are really critical in that case, especially when they get bigger and bigger and bigger, yeah.
When it comes to this microwire technology, is it also possible to connect on both layers, that you have, for example, a component embedded, connected from bottom and top?
It depends. So yes, that's already being done. So I didn't go into very details here, but for example, MOSFETs, when you have like a backside connection needed, it depends on the die what you do. So there are several ways to get this doing. If the die, for example, has copper on the front and the backside, and you have only that die, so you can have a very tight tolerance and a tight planning in your core, you can actually connect it on both sides with microwires. Another thing what you can do is, for example, placing the component on a very thin core. Especially, for example, let's take the example MOSFETs. You can sinter them onto this core. And when you use like a 100 micron core, you can already make a microwire in that 100 micron core. So connecting the sinter part, and from the other side, make the microwire on the top for a source and for the gate, for example, connect it there. And you still have the double-sided connection. So it may be possible, yes. It depends on the component, depends on the setup and so on, but there are ways to do this.
Thank you for your presentation. I'm enjoying it. Question for you for multi-layers of embedded. Are you seeing it from 2 sides, all on one
So
PCB?
we have one, yes, it's being doable, but we have one restriction at the moment. Due to the fact that we assemble very, very thin cores. So the thinnest cores we assemble is either a 100 micron FO4 core, or for the microwire technology, it's even a copper foil, which we assemble, which is on 18 by 24 inch, Yeah, it's flexible basically. So we need to have carriers, and therefore we cannot do a backside assembly of this core yet. So if you want to have multiple layers, you need to assemble multiple cores.
At different depths.
Different depths would be possible. So, but that's a really, from a three-dimensional planning, then it's really getting critical. So we even have applications where you have two cores assembled, one going top, one to the bottom. And this is where really step and so on comes into place and make collision checks and stuff like that, yes.
Sorry, one more question.
problem.
You were talking about the reliability of such PCBs in the very beginning. So I see the point when everything is manufactured and tested that the reliability is way better. But how about the fail rate during production? Because you have more processes involved, so are they on the same level of security as normal PCB production already, or is there a higher risk involved at those inner layers?
Basically, there is a higher risk involved, yes, because you have more process steps. What we try to do is that we run all these jobs on a higher level, basically in fab, so that you take more care. So we, for example, in our process flow, we implemented that each core, it doesn't matter if it's ordered by the customer or not, is being treated and is being looked on in the AOI, for example. So we do what we can do to test everything to the max. We do a lot about processes, so the processes are getting better and better. Regarding yields, to just give you figures, it depends really on the complexity of the components. If you have like a packaging application with one component, we are in yield rates up 99.5% already. The more complex the board will get, the yield will go down, but still we need to stay in the area of 95 plus.
Anyone else? Oh, yeah.
Just wait for the mic, please.
Yeah, you gotta wait for the mic, please. Sorry.
I have one additional question relating to logistics. Do you take ownership of all the components, or how does that work in production?
There are different models. So for the solar technology, at the moment we are working together with a partner. So this is an EMS which we work with, which has additional capability to do this. So the components are either bought by him. There are some components which cannot be bought. If this is a customer designed ASIC or stuff like that, this will just be provided by the customer. So the ownership still belongs to the customer. And the question always occurs, how do you deal with that? Well, basically it's contracts. So in the contracts you will define which will be supplied by a customer, which will be supplied by us or the EMS. So it's application specific and customer specific.
This man seems to know what he's talking about.
I was wondering what happens to the solder on the inner layers if the cavity fills with resin completely and then expands again during the reflow process of the components on the outer layers. Yep. Doesn't that create a lot of mechanical stress on the solder on the inner layer since it can't expand then?
Well, basically that's a good point. We tried to look on this a lot, but you actually, it's hard to see it. So what we can do is we can look on it before assembly, after assembly, but during assembly it's hard to look inside, so you only can simulate this. And during simulation, what we did together with a university in Germany is that, yeah, there is some mechanical stress, but not enough that it gives you a force for delamination. So the solder inside, it will remelt, but there is no atmosphere inside, so it just melts and hardens again. But we didn't see anything up so far, maybe, but the simulation showed that the force which acts on the prepreg actually is getting weak as well, so it can take the force as well.
If I got one more, yeah, John, let me give you the mic. And then we'll get you guys out of here. We're only about 5 minutes over so far, so we're all right.
Excellent presentation. Not sure if you covered it already, but impact on pricing. When is embedded component practical, and roughly how much more is it expensive than a traditional exterior mount component?
I tried to cover this already in the beginning of the presentation. And what I always like to say is use it when you need to use it. But that's just like in any other technology. You're not using HDI technology if you don't need it. You're not using rigid flex technology if you do not need it. You've seen some advantages in the beginning. So most of my customers, they have some needs which they cannot fulfill with standard PCB technology. And covering the price topic, I cannot tell you that it's like 20% more expensive or 50% more expensive, because it depends on the component you put inside. The more components, it's just like on the outer layer. It's an assembly price. The more components, the higher the price for the assembly. Then you have the components themselves. But this is basically easily calculated because the assembly process is close or like comparable to the outer layer assembly. As I said, the only additional cost you get is for the solder technology. When we look on that one, for example, is you have an additional screen printing process for the solder mask. You have the solder surface, but that is almost not additional because you need an adhesion promoter anyway. So you cut out, or you leave out one adhesion promoter and put on the other one, which is the solder resist as well. And then you have your cutouts in the prepregs. And there it depends on how thick the components are. The more you have to cut out, the higher the cost. We can stack, for example, prepregs. So if it's 5 prepregs we need to cut out, we can stack them and cut them out all in one. Either we route them, or in higher volumes we punch them. So it's not one prepreg after another. So, but that's basically all the additional cost. And then it depends on the application. So this goes from 10 to 15% in addition to up 100, 150%. It really depends, so I cannot give you a precise number. If you want to have a precise number, we could talk in one-on-one, have a look on your application and do just a quick calculation and give you a ballpark price.
Is there a volume you can recommend?
Mike?
He asked if there was a volume that he could recommend.
So regarding the volume, well, we are lucky to have different fabs. So we start from prototypes. The minimum what we do normally is our prototype panel occupies a 12 by 18 inch, and we need to have 2 of those. So that's where we normally start. And volume at the moment, yeah, when it comes to millions of this big pieces, then we might get into problems. But like my management says, well, if the need is there, we will create the answer. Yeah.
I like this guy. So, all right, yeah, Juergen, that was outstanding. Really appreciate it. So if y'all want to catch up with Juergen, he's still going to be here, I'm assuming, the rest of the day. Yeah. So definitely catch up with Juergen. And he's actually, Werf is one of our sponsors as well. So we appreciate your sponsorship and, of course, your presentation. It's lunchtime. So go have lunch, and then we'll get going. The development course is next at 1:30. So pick your course, and we'll see you at 1:30.